Okay, so the last video was about simple pendulums, and we talked about one of the assumptions that you have to make, and that was that this angle is really small. We also have a second assumption, and the string has no mass, so that all the mass is located at this point. Okay, but it turns out that there's also a kind of system that we'll call a physical pendulum, when the mass isn't all at the end. Okay, and so there's mass all throughout that's oscillating. And the reason that we can't use the formula for a simple pendulum here is because in order to derive this formula, we had to say that the moment of inertia here was mr squared. We treated this as an oscillating point. Here, though, it's not just a point, there's mass all throughout it. And so I, in this case, would not be equal to mr squared. So we're going to rederive this formula for situations where we have a physical pendulum. Okay? So let's remember that our goal was to get alpha to be equal to negative omega squared theta. Our goal was to get here. Okay? And so we said that I alpha equals, so for a physical pendulum, we have a torque acting at the center of mass. Okay? So we have a force mg acting at a distance that we'll say is h, this distance h between the center of mass and the point of rotation. And so, and then we'll say that there's some angle theta here. Okay? And so the sum of the torques would be equal to the gravitational force acting times the distance away, h, times the sine of the angle between the force and the radius. Okay? And so alpha then, it's a negative torque, we'll say. And so alpha is equal to negative mgh over I times sine theta. Okay? And so, from here, remember last time we said that when theta is really small, that sine theta is approximately equal to theta. So alpha equals negative mgh over I times theta. So that omega is equal to the square root, I'll slow down, omega squared, right? This piece here is this piece here. So omega squared equals mgh over I, which means that omega is equal to the square root of mgh over I. Now that period is equal to 2 pi over omega. So then the period of a physical pendulum would be equal to 2 pi over the square root of mgh over I, which then can be simplified 2 pi square root of I over mgh. Okay? And this is a more general formula for the period of a physical pendulum. So let's try this out with an oscillating system. Let's say that we have an oscillating meter stick connected at one end. It's a meter long, has a mass of 60 grams, and I want to know what the period of it is. Okay? Remember, its center of mass would be located right here. Okay? And that would be 50 centimeters down. And for a moment of inertia, since it's a uniform rod, we need 1/12 ml squared. And since it's not rotating about its axis, we have to use mh squared. Okay? So, let's go ahead and substitute in these values and find the period of this physical pendulum. So we get t equals 2 pi square root of 1/12 ml squared plus mh squared all over mgh. M's will cancel out. Okay, we get 2 pi square root of 1/12 times 1 squared plus 0.5 squared over g times 0.5. And so we get a period of about 1.64 seconds. Okay? So let's compare this now to a simple pendulum. So the question I have is, well, why can't we just use a simple pendulum that is 50 centimeters long, or 0.5 meters, okay, to do this same process? Well, what would be the period of a simple pendulum with a length of 0.5 meters? Okay, we punch this in, and here we get a period of about 1.42 seconds, okay? Which is a pretty significant difference. It's a difference of about, that's a variation of about maybe 13%. And so the reason why is that something that has mass more distributed would, with all this mass out here, this mass is more difficult to oscillate than this mass in here. And so that's why it takes longer, because gravity has to work harder to cause it to rotate. Okay? Here's another question for you. What would happen for a physical pendulum if it was oscillating at its center of mass? Okay? Which means that the distance away between the point of oscillation and the center of mass, what would happen when we made that distance equal to 0? What would happen to those oscillations? Well, what you would notice is that at that point h would be equal to 0, which means that we would be dividing by 0, which means that it wouldn't oscillate. And the reason why is there is no gravity at that point, can't exert a torque, since the center of mass is located at the point of rotation. Alright, and you should also think about the fact that as h gets smaller, that period gets bigger and bigger and bigger and bigger. Okay?